This is slide number 59 and I am your presenter Asloob Mudassar. Incoherent imaging transfer function. For a diffraction limited aberration free incoherent imaging system, the image intensity capital I subscripted I as coordinates of u and v, which are the imaging coordinates, is given by equation 20 we have discussed already and is reproduced below in equation number 39. So you see that we have in the equation this integral contains absolute square of kappa as a function of u minus zeta 1, v minus eta 1, and it also contains ig, which is the geometric optics image as a function of zeta 1 and eta 1, and beta is some constant which and this equation has been described in the theory given after equation number 20. And you know that we can abbreviate this equation as beta times ig as a function of u and v convolved with the absolute square of kappa. And you know that kappa is actually the amplitude point spread function, or the absolute square of kappa is actually the intensity point spread function. So the convolution of the kappa, absolute square of kappa, that is the intensity point spread function, with the geometric optics image will give you the intensity at the image plane as described by in equation number 39. So absolute square of kappa is the intensity PSF, or the intensity impulse response under incoherent imaging system. Ignoring the constant beta, the Fourier transform of equation 30 number 9 is given by. So here we are taking a Fourier transform of both sides of equation number 39. So you see that on the right hand side we have two terms which are convolving with each other. So the Fourier of this one will be the Fourier of a first quantity multiplied by the Fourier of the second quantity according to the convolution theorem. So the you see that the Fourier operator on the absolute square of kappa will be represented by capital K subscripted as in and as a function of fx comma fy, and the Fourier operator operating on ig, that is operating on the geometric optics image, will give you capital G with the subscript of small g as a function of fx comma fy. And you know that on the left hand side we have the Fourier transform of the intensity image represented as capital G, and small subscript represent the image plane, and you know that again it is a function of fx and comma y. So equation number 40 can be read, and you know that the equation number 40 correlates two very important quantities. One is capital GG and the other is capital GI. So these two quantities are the spectra of the image plane of the intensity at the image plane, and also at the of the intensity at the object plane, that is the geometric optics image. And you know that kappa K in actually is the weighting factor that is relating the two important quantities. So you see that here Gi of fx comma fy is the normalized spectra intensity of the image, and the capital G small g as a function of fx comma fy is the normalized spectra of geometric optics image. K in as a function of fx comma fy is the normalized Fourier transform, or the Fourier spectrum of intensity point spread function, and is known as the transfer function of the incoherent imaging system, or optical transfer function, and abbreviated as OTF. Gi of fx comma fy and Gg of fx comma fy are related through the complex weighting factor provided by K in as a function of fx comma fy. Subscripted in stands for incoherent. Equation number 41, 42, 43 give the normalized spectra, and the normalization constants in the denominators of each equation are the sum over signal values in the respective cases. For example, look at equation number 41, 42 and 43, where we have defined the normalized spectra of Gi, Gg and K in respectively. So you see that, let me read the first equation 41. On the left hand side we have Gi, capital Gi as a function of fx comma fy, and on the right hand side in the numerator we have the Fourier integral giving the Fourier transform of capital I subscripted as small I as a function of u and v. And you know that here we have divided it in the denominator by some term. The denominator term can be obtained by substituting fx is equal to 0 and fy is equal to 0 in the numerator. Then you will get the denominator, that is when fx is equal to 0, fy is equal to 0, it means that we are talking about the 0th order frequency. So the denominator is actually the value of the spectrum at the 0th order frequency. And you know that the same things also valid for equation number 42 and 43 respectively. Denominators in each case can be obtained by setting fx is equal to 0, fy is equal to 0 in the corresponding numerators. Thus, the normalization constant in each case is equal to the total energy contained in the 0th order frequency of the corresponding Fourier spectrums. The energy in the 0th order frequency in a Fourier transform comes from the background of the corresponding image. So you see that if you have an image and if you take the Fourier spectrum of that image, then the 0th order, then the energy in the 0th order will come will belong to the background information in the image. By international agreement, K in as a function of x, fx and fy is known as the optical transfer function, OTF. And its magnitude, which is the absolute value of K in, is known as the modulation transfer function MTF. MTF is a measure of the contrast or visibility in an image through a lens. Here we are not going to define the MTF in with respect to K in, which will be defined and which will be explained later on in some slides. But here we are going to define MTF as a measure of contrast or visibility in an image through a lens. The contrast or visibility is defined by equation 44. So the visibility is equal to I max minus I minimum divided by I max plus I minimum, where I max is the maximum value of the intensity in an image and I minimum is the minimum value of intensity in an image. So let's explain contrast in relevance with some example. So look at this example. There are two in image A we have an image which is actually the original object, and the image in B is actually the image of A through the lens, and C is actually the cross-sectional view of the image in A, and D is the cross-sectional view of the image in B. So A is our original object and C is the original cross section and B is the image of A through the lens and D is of course the cross sectional of the image through the lens. So let's explain the caption of this one. Contrast reduction in an image through a lens. So you see that here we are going to explain the contrast reduction. So you see that if you look at object A, the contrast is very high. Even at the rightmost part the lines can be resolved, the contrast is higher. But you know that in B, if you move from left to right, you will see that the contrast will keep on decreasing as we move towards the high spatial frequencies. And you know that at the highest mode you will see that it is hard to resolve the lines between them in the last band. And you know that this has been explained also in figure number D. Look at figure number D. You know that if you compare C and D, you will see that in D the sharp edges are rounded slightly. And also you will see that the contrast is going to reduce as we move towards the right. And you see that especially in the right two bands, the minimum image value has risen up and the maximum value of the image has decreased, which means that the contrast has lowered over here. So contrast reduction in an image through a lens. Original object in A after passing through an imaging lens is shown in B, with the respective cross sections are shown in C and D. The image in part B has a contrast that reduces with the increase in spatial frequencies of the image towards the right, which is obvious from part D. The edges are rounded as seen clearly where the spatial frequency is lower, left side of the image, and the brightness is reduced in the rightmost part of the image where the minimum signal value has increased. The contrast is lower on the right hand side in comparison with the contrast on the left hand side of the image in D. MTF thus decreases towards the right side where the spatial frequency increases. So you see that we have explained the MTF or the visibility of these images, especially the cross sections through A and B given in C and D. And we have compared the figure in C and D in terms of the sharpness, that is the sharpness in degree has decreased in figure number B because the edges are rounded, and the another thing is that the contrast has fallen as we move towards the higher spatial frequency end. So the MTF, you know, that can be calculated and can be seen very easily through the cross sections of the images. Next, we want to relate the coherent transfer function Kc with the incoherent transfer function Kin. The former is known as the amplitude transfer function and the later one is known as the intensity transfer function or the optical transfer function. So Kc is actually the amplitude transfer function and Kin actually the intensity transfer function or the optical transfer function, also known as OTF. The two transfer functions are related to a common quantity known as the point spread function or the impulse response kappa. So kappa is the quantity at through which the Kc and Kin both are related through equation 30 and equation 43, which are reproduced below respectively in equation number 45 and 46. So you see that in equation number 45, the coherent transfer function is related with the Fourier transform of kappa, whereas in equation number 46, the incoherent transfer function is related with the Fourier transform of the absolute square of the kappa, that is the intensity point spread function. And you know that we have shown in case of Kin on the right hand side, we have shown the normalized value of the quantities. And you know that in the last step of the equation number 46, we have shown explicitly in the numerator that it is the Fourier transform of the absolute square of kappa, and again divided by the normalization constant. We have explained these constants earlier. So you see that we can connect the two, that is we can connect Kc and Kin through the kappa, because you see that Fourier transform of kappa appears in equation number 45 and also the Fourier transform of absolute square of kappa appears in equation number 46. Let's see how we connect these two quantities, that is Kc and Kin in the coming slides. Let's evaluate the Fourier transform of absolute square of kappa. The Fourier transform of absolute square of kappa is equal to Fourier transform of kappa multiplied by the complex conjugate of kappa. You know that these two quantities are multiplying on the right hand side and the Fourier operator is outside the curly bracket. So the operator will operate on first kappa and there will be a convolution sign with the second kappa. You know that here we have applied the convolution theorem. That is, when two quantities are multiplying, the Fourier transform of the product of these two quantities will be equal to the Fourier transform of first quantity convolved with the Fourier transform of the second quantity, which we have done in the second step. Okay, now let's evaluate these two Fourier transforms. The Fourier transform of first kappa is represented by Kc as a function of fx comma y. Then there is a convolution sign over here, and you know that the Fourier transform of the conjugate of kappa value is equal to Kc, the conjugate value of Kc as a function of fx comma fy. So you see that now we can represent okay. So you see that the convolution, let's give these two, you know, that are the symbolic form of convolution. Now you know that their correct definition is given by through the integral, and below in the second step we have shown the integral definitions of the convolution of the two quantities, that is Kc and Kc conjugate. So look at this one. We have taken arbitrary constants p prime and q prime, and then you know that we have fx minus p prime and fy minus q prime, because fx and fy exist on the left hand side, because we are taking the Fourier transform of the space variables u and v, and then you know that when you take the Fourier transform of the space variables, you will get fx and fy on the right hand side. So you see that here, that's why we have used fx and fy on the left hand side, and the variables p prime and q prime are also shown, and you know that dp, the integration is with respect to dp prime and dq prime. So through the integration, p prime and q prime will vanish out, and the integral will survive with two variables fx and fy. And you know that this is the definition of the convolution of the two quantities in integral form. So you see that this the conjugate of a kappa, the conjugate of capital Kc, which is the transfer function, which is the transfer function. And you know that this quantity has been shown over here, but here we have, because this quantity is an even quantity, we have reversed their coordinates. That is, we have p prime minus fx comma q prime minus fy. Now you know that this becomes the definition of the correlation integral. So equation number 7 in the second last step will now give you the definition of the autocorrelation of the kappa of the capital Kc, because you saw that this is the definition of the integral gives you the definition of the autocorrelation integral. So that's why we have written in the symbolic form in the last step, that is Kc as a function of fx comma fy autocorrelated. This is the asterisk sign which represents the autocorrelation with the Kc again as a function of fx comma fy. So it means that the Fourier transform of the absolute value of a kappa on the left hand side of equation number 47 is equal to the autocorrelation of Kc. That is, Kc will autocorrelate with Kc. And you know that we have shown it in the symbolic form, and its actual form is shown in the last step in the integral form. So for a diffraction limited aberration free system, Kc is real, positive and even. Using the even property of Kc, the second last step was written. So you see that from the second step from the top and the second last step from the bottom, we have used the property that the Kc is an even function, and the conjugate of Kc is also an even function. So you see that the property of the even function has been used, and that's why the variables in the second step, which was fx minus p prime and fy minus q prime, has been converted to p prime minus fx and q prime minus fy. Thereby the convolution integral has been converted into the autocorrelation integral. And you see that we have written the autocorrelation in equation number 47 in the last step in the symbolic form. In order to keep the derivation extendable to the systems with aberration for future use, we are assuming that Kc is in general complex as far as the derivation is concerned. The denominator in equation number 46 according to Rayleigh theorem can be written as. So you see that here you have the denominators over here in equation number 46. We can also represent this because we have represented the numerator in terms of the Fourier frequencies, in terms of the Fourier domain. So you see that the denominator can also be represented in the Fourier domain using the Rayleigh theorem, and which we have shown in equation number 48. So you see that this is a very famous theorem which we have already discussed and is regarded as the Rayleigh theorem. Equation 48 states that the total energy contained in the intensity point spread function is equal to the total energy contained in its spectrum. So you see that we can replace the above equations, that is, we can replace the denominator in equation number 46 with the right hand side of equation number 48. So using equation number 48 into the denominator of equation 46 and using the second last step from equation number 47 into equation number 46 gives. So we have written k in as a function of fxy is equal to the integral which we have written from equation number 47. This is what we have written, and now we have divided the numerator, and we have also written in its corresponding in the Fourier domain the variables that we have used in the Fourier domain, that is p prime and q prime, both in the numerator and in the denominator. And you see that we have used this definition, that we have used the second last step in the integrals. So we have used for equation number 47 and equation number 48 to write equation number 49. In order to make the numerator term symmetrical, you see that the term in the numerator is not symmetrical. One has the variable p prime q prime, the other the k conjugate has the variables p prime minus fx, q prime minus fy. In order to make the numerator term symmetrical, that is to make kc and kc conjugate positioned in opposite coordinate planes, we introduce the following change of variables in equation number 49. That is, p prime will be replaced by p plus fx by 2 and q prime will be replaced by q plus fy by 2. So making these changes, we get this. So you see that now it makes some sense that kc and kc conjugate are positioned in opposite coordinate systems. We can also change in the denominator. We can use p prime replaced by p and q prime replaced by q prime, and q prime will be replaced by q because the value of the integral remains unaffected. So we can change the denominator also, which we have shown, which we shall show next. Okay, numerator in equation number 51 can be recognized as the autocorrelation function of the coherent transfer function. That is these two terms. That is in the numerator, autocorrelation of these two terms. We thus conclude that OTF, or the transfer function of the incoherent imaging system, is the normalized autocorrelation function of the coherent amplitude transfer function. Equation number 51 provides a direct relationship between the two transfer functions. So you see that this is the equation which provides a direct link between the incoherent transfer function, that is Kin, and with the coherent transfer function, that is Kc. So equation 51 can be derived for an aberration free system, but it is equation number 51 has been derived for the aberration free system, but you know that it is equally valid for a system with aberration, and we shall also discuss the system with aberrations later on. So here we have plotted k in values. So you see that k in, you know, that has a function which tapers off, and it is very much similar to the triangular function, you know, that which is linearly decreasing towards the edges. And you know that notice its width on both axes, which is 4f0y along the y direction, that is along fy direction, and 4f0x along the fx direction. And you know that in the coherent transfunction it was 2 times f0x along the fx direction and 2 times f0y along the fy direction. And you know that here in the incoherent case it is twice of that. That is, the cutoff frequencies are twice that of the coherent transfer function. So incoherent transfer function has cutoff frequencies which are equal to twice the cutoff frequencies in the coherent case. And you know that here we have given its the cutoff frequencies has also been represented in its variables form, that is 4wh over lambda zi. And you know that on the y variables we have 4wy or divided by lambda zi. And you know that here the object dimensions, object was rectangular, that is our aperture was rectangular with the dimensions 2wx along the x-axis and 2wy along the y-axis. And you know that here we have these quantities which we have shown, that is, we have shown the cutoff frequencies. The important point is that it tapers off and it is decreasing linearly as the figure shows, and moreover its cutoff frequencies are twice that of the cutoff frequencies we encounter in case of coherent transfer functions. OTF of a diffraction limited system with a square lens pupil, but not with the square lens pupil, but you can see that with a square lens pupil, because the dimensions are different. You know that here we are using wx and here we are using wy. If you set wx is equal to wy, then we can say that it is the OTF of a diffraction limited system with a square pupil aperture. But in this case you will see that you will say that it is for a rectangular lens aperture having dimensions wx and wy from the center, or 2 wx or 2 wy along both x axis and y axis. Coherent transfer function has the same shape as that of the pupil aperture function, whereas the incoherent transfer function has a triangular shape. So you see that in the coherent case we have noticed earlier that the shape of the coherent transfer function is the same as that of the pupil function. But you know that here in the incoherent case we observe that it is a triangular shape. That is, this coherent transfer function has the triangular shape. The cutoff frequency for the incoherent transfer function is twice the cutoff frequency due to the coherent transfer function. Incoherent transfer function tapers the Fourier frequencies, whereas the magnitude of the Fourier frequencies remains unaffected in the coherent transfer function. Properties of incoherent imaging transfer function. The first property is given in equation number 52, that is K in at the zeroth order frequency. The K in has a value equal to 1 because we have already normalized K in. So the normalized value is equal to 1 at the zeroth order frequency. The K in conjugate at the coordinates minus fx comma minus fy is equal to K in at the coordinates fx comma fy. And equation number 54, that the absolute value of the K in at any other frequency fx comma fy is always less than equal to the absolute value of the K in at the zeroth order frequency. So here we are going to establish equation number 52 first. Let's use equation number 59. So you see that we have shown equation number 59, but with this equation we have shown that fx is equal to 0 on the left hand side, fy is equal to 0 both on the left hand side and on the right hand side. So you see that if with these one you have the second step given over here. So you will see that now we have Kc and we have Kc conjugate in the numerator, and you know that we can write it as absolute square in the numerator, and you know that now the numerator and the denominator are exactly equal to each other, will cancel out, will give you 1 as in equation number 55. Now let's establish equation number 53, which was this one. In equation number 53, let's use equation number 51. Where is equation number 51? This is equation number 51. So we are going to use equation number 51 in order to establish the property given in equation number 53. So here we have shown, you know, that equation number 51. Let's take the complex conjugate of both sides. So we have shown the complex conjugate over here, and on the right hand side in the numerator we have also shown the complex conjugate quantity outside the bracket. There is no need to take the complex conjugate in the denominator because the denominator is always a squared quantity. So if you apply the conjugate limit now, this has been shown in this one, that we have shown the conjugate on the first term, and of course the conjugate of conjugate is, you know, that the same term. So we have shown these two terms over here. Now you see that we are making the substitutions, that we are replacing fx by minus fx and fy by minus fy on both sides. And if you do this one, you will see that you will get the right hand side, which is the same as we started with. So you know that the right hand side is the same quantity, that is K in, as if you look at this one. For example, equation number 51. So equation number 50, the only reason is that we have here in the last step that we have Kc conjugate over here and Kc over here, but you know that this product doesn't matter. So you see that in equation number 56, the equation number, the right hand side of equation number 56 is the same as the equation number we have shown 51. And you know that we can write the right hand side by k in as a function of fx comma fy. So you see that here we have proved the property. The second property given in equation number 52 has been proved. Thus k in conjugate at coordinates minus fx comma minus fy is equal to k in at coordinates fx comma fy. Similarly, we can also prove that k in conjugate at fx comma fy is equal to k in at fx minus fy, as in equation number 58. Here k in is equal to its conjugate in opposite coordinates and is Hermitian. So from equation number 46 we can write k in. So this is again, you know, equation number 46, that is the numerator has the Fourier transform of the absolute square of kappa, and you know that in the denominator we have also the absolute terms of kappa. So the right hand side is, you know, that is a positive and a real quantity. So we can say that the Fourier transform of a real and positive quantity is a Hermitian. So you see that this is a general step, that is a general argument that we have derived from this one, that is the Fourier transform of a real and positive quantity is a Hermitian, and the property of the Hermitian has shown above. Now we have to establish the third quantity, that is the absolute value of k in at any other frequency fx comma fy is always less than or equal to the absolute value of k in evaluated at the zeroth order frequencies. That is fx is equal to 0, fy is equal to 0. To prove this one, we are using the Schwarz inequality, which is listed in equation number 59. So look at this quantity. We have the absolute square of the integral of two quantities x multiplying with fy, and you know that this is less than or equal to the square of the absolute square of individual integrals if y is not equal to epsilon times the conjugate of x. But if the maximum value, that if the left hand side can take the maximum value equal to which could be equal to the right hand side only if y is equal to epsilon times the conjugate of the other quantity. So you see that here the equality will hold under this condition, that y can be written as some value times the conjugate of the other quantity. So you see that we shall use these quantities, this Schwarz inequality in order to establish over this quantity that we have shown over here. That is the absolute value of k in at any other frequency is always less than or equal to the absolute value of k in at the zeroth order frequency. So we shall formulate over these quantities separately, and then we will construct. So let's see that how we utilize this Schwarz inequality for our system. So you see that here we record that x as a function of p and q is equal to kc as a function of p plus fx by 2 comma q plus f by 2, and y is equal to kc conjugate, which has the coordinate p minus fx by 2 and q minus f by 2. So you see that here what are x and y? We have established that x and y are these two terms on the right hand side, which we have explained in equation number 60. So substituting these values and writing the right hand side of this one, that is right hand side of equation number 59, by substituting these values we have written equation number 61. So now let's make the transformations, that is p is replaced by minus p, q is replaced by minus q, and calculating the derivatives and the limits and rearranging the integrals, we get this. So we have changed these variables, changed the limits, changed the derivative, and then rearranged the integral. We obtain this integral, and you know that we have kc with p plus fx by 2 and q plus fy by 2 and the absolute of this quantity. And similarly on the right hand side there is an integral that contains the absolute square of kc conjugate with the variables minus p and minus fx by 2 comma minus q minus f by 2. And using the property we have already established in equation number 57, that is this property. So using this property given in equation number 57, we are going to change the second integral over here, and which we have shown in the last step of this one after using the property I have just mentioned. So the right hand side of this one equal to this. So you can see that both are Kc, and we have removed the conjugate term, and because we have replaced the conjugate term with its term without conjugate, that is Kc, using the property given in equation number 57. So this is the right hand side we have evaluated, that is we have evaluated the right hand side of equation number 59. And you know that these two integrals are the same, so we can take it the square of these two. That is, we can write one integral and we can take the square of that one, as shown in equation number 62. The inequality in equation number 59 takes the form. So you see that we have evaluated the left hand side, the right hand side, which we have shown in equation number 62. And then you know that we have already defined capital X and capital Y, which we are going to submit over there, which we are going to substitute in equation number 59. So we are using 59, we are making these substitutions of equation number 60 in equation number 59 on the left hand side, and the right hand side is what we have evaluated over here, that is in equation number 62. So using these two we have obtained the inequality, that is the Schwarz inequality will take the form as we have given in equation number 63 in our own variables, that is Kc and Kc conjugate on the left hand side and both Kc on the right hand side. And you know that there is an inequality sign which shows that less than equal to. To use this inequality in equation number 51, which is equation number 51, let's see where we want to use this inequality. This is the inequality. So in the denominator, if we use this inequality, then you know that we can write this equation number 1 after using that inequality in the following form. So we are using this inequality over here, and you know that we are addressing the numerator of that quantity there. And you can see that we have the square root and then we have the absolute square of that quantity, because we have taken the absolute value of the input also there. And if you look at this quantity, you see, and then in equation number 64, when we go from equation number 64 to 65, what we do is that we replace the equality with the inequality. So k in mod, the absolute value of k in mod is less than equal to the quantity on the right hand side. And you know that the numerator is now exactly the same as the denominator. Both terms will cancel out, because here the square root will cancel out with the square root, and then you know that the rest of the quantities are the same. So the numerator equals the denominator will cancel out, will give you 1. So it means that here the absolute value of k in as a function of fx comma fy is less than or equal to 1 as given in equation number 65. So for the equation number 65, we can write that the absolute value of k in as a function of fx comma fy is less than or equal to 1. But you know that we have proved earlier in equation number 50, perhaps 52, let's see, okay, 52, that k in at 0, 0 is equal to 1. And now we have established that k in at any other frequency, the absolute value of that one is less than or equal to 1. So combining the two, we can say that that the absolute value of k in at any other frequency is less than or equal to the absolute value of k in at the 0th order frequency, which is equal to 1, as given in equation number 66. So thus the third property is proved. This indicates that the magnitude of the incoherent transfer function at any frequency is smaller than its value at the 0th order frequency. So this is the end of slide number 59.